Bhardwaj here, telling us about the categorical Landau paradigm. Go ahead.
Yeah, so let me begin by thanking the organizers for inviting me here. It has been a wonderful workshop, and I would like to end it on a high note. So I want to talk about categorical Landau paradigm, which generalizes the usual notion of Landau paradigm. The word categorical is there because it applies to not only just group symmetries as traditional Landau paradigm, but it applies to non-invertible symmetries, which are not of group type and are described by fusion categories or fusion higher categories. So in this talk, I will mostly be focusing on the one category case, the traditional categories, which are fusion categories. They describe non-invertible symmetries in 1+1 space-time dimensions. But towards the end of my talk, I will discuss some extensions to higher dimensions as well, to fusion 2 categories, which describe symmetries of 2+1 dimensional systems. So I want to phrase Landau paradigm in a certain way, which makes it amenable to generalization to arbitrary fusion categories. So let's recall the traditional Landau paradigm using the example of 1+1 de-Ising model. Recall that in the Ising model, there is a parameter that one can tune. There is a critical point, and depending on the sign of this relevant deformation, you can either flow to a ferromagnetic phase or a paramagnetic phase. So in terms of the spin system, you have either two degenerate ground states on one side. So you can either have all spins up as one of the ground states or all spins down. And on the other side, there is a unique ground state, which is for the poly X operator. So which is an eigenstate for the poly X operator, you can denote it like this. Or it's a combination of all the ups and downs. Right, so there are two phases, which are known as ferromagnetic and paramagnetic phases. And they're characterized by spontaneous symmetry breaking of a Z2 symmetry. So we have a symmetric group in the model, Z2. And in the ferromagnetic phase, this is spontaneously broken. While in the paramagnetic phase, this is not spontaneously broken. Or we also refer to it as the trivial phase with Z2 symmetry. So now so one also typically associates order parameters with this scenario. So at the critical point is described by the Ising CFT, which has two kinds of operators that would be of concern for us. So there is the spin operator denoted by sigma. This is just a traditional genuine local operator. And it has the property that it carries a non-trivial charge under the Z2 symmetry. So on the left-hand side in the ferromagnetic phase, this operator acquires a non-trivial wave. While in the paramagnetic phase, it has a trivial wave. And for our purposes, let's also look at the operator, another operator, which is not a genuine operator, but it's an operator in the twisted sector for Z2 symmetry. So it's also known as a non-genuine operator. It's a local operator that comes attached to a topological line operator. This topological line operator generates the Z2 symmetry. And I'll denote it by P, the generator of the Z2 symmetry. And the role for mu is reversed. So mu takes a non-zero expectation value in the paramagnetic phase, while a trivial expectation value in the ferromagnetic phase. So the two phases can be described by some interesting operators which talk to the Z2 symmetry. In one case, you just have an operator which is charged. In one case, the operator is in the twisted sector, but it's not charged. And depending on what webs these operators get, we get the two phases. So one could have asked if it's possible to have both these operators as condensing in a phase. So is there some phase which is missing over here? And it's well known that it's not possible because there is some braiding. So there is a non-locality between these operators, which I will denote by saying there is some non-trivial braiding between them. So what it means is that if I take the sigma operator and move it around the mu operator, the correlation function does not remain invariant because it passes Z2 symmetry line and it obtains, because of the charge of this operator, the correlation function changes by a sign. So it's not possible to condense both of them simultaneously. You can either condense sigma or condense mu. So there is no missing phase. In this Ising model, we have realized all the possible phases that one can think of. Let's state it a little bit more abstractly. So let's take ourselves away from sigma and mu and just keep into account the properties related to symmetries. So let's say for the essential property of this operator sigma was that it's charged into the Z2 symmetry. So this one is charged and this one is twisted. Both of them cannot simultaneously, if we have two operators of this kind, they cannot be simultaneously condensed, but we can condense one or the other. If we condense a charged operator, we get two degenerate vacua because I have now two topological operators in my infrared system. Yeah, and this acts as a way to detect the two ground states. And if mu is condensed, then that means that the line operator P can be made isomorphic to identity, or it can just be, it can always be removed by breaking it by generating some topological operators mu in the infrared. So in that case, the Z2 symmetry is generated trivially, or we are in the trivial phase. So let me pause to see if there are any questions at the moment. Okay. So that's all good. So yeah, so now let me talk about generalizations of this scenario. So let's see what happens for Z4 symmetry. So first of all, we want to decouple ourselves from the dynamics, from concrete dynamics of what theories there are, but we just want to talk about symmetry properties. So what kind of operators there can be. So first of all, you can have operators which have charges 1, 2, or 3 under the modulo 4 under the Z4 symmetry. So let me denote just these charges. So there is an operator of charge 1, which I can denote the charge by E, E squared and E cubed, which are charge 2 and charge 3 operators. Then one can have operators which are in the twisted sector, which are again of 3 kinds now. So you can have either P, P squared, or P cubed, where P is the generator of Z4 symmetry, and operators lying at the end of it, which are uncharged under Z4. So let me denote them by M, M squared, and M cubed. And then there are products of these. So these are all the possible kinds of charges that can exist in a Z4 symmetry. And then we can now ask, what's the non-locality between them? And the non-locality takes the form, so it's something like, so this is the form of the non-locality. And we can now look at what are the possible condensation patterns. So let's look at if we condense E, we have to condense E squared and E cubed as well. So this is one sort of condensation pattern. So I say if I have my condensed charges are all of E type, I cannot condense any of the M types because of the braid. And so if I have all of these operators, you can recognize that now we will have 4 degenerate ground states because I can distinguish them by finding by measuring these operators which are charged, which have these kind of charges. So this you can recognize it as to be the Z4 completely broken phase. Now we can look at other kinds of condensations. So suppose we do all the M ones to be condensed. So in this case, we only have twisted sector operators. So in the infrared, we have operators of this type. We have all the symmetry generators can be made trivial or can be opened up by some topological local operators. So the Z4 symmetry acts completely trivially. It's not broken at all. So this would be the trivial phase. But the traditional Landau paradigm tells us that there's one more phase to talk about where Z4 is broken down to Z2. So that one is also included if we condense these ones. So we want to break down Z4 to Z2, which means that the Z2 subgroup inside Z4 acts trivially. So we need a twisted sector operator at the end of P squared to make P squared trivial. And then we need something which carries a charge 2. So we have another operator which carries a charge 2 under Z4. And this is what we can call as Z2 SSB phase of Z4. So this recovers all the classification, the traditional Landau classification for Z4. But now you may wonder that there are actually some other things over here. So one can, instead of condensing all of these, one can try to condense some subset of them. So one can try to condense just 1 and E squared. What happens in this kind of situation? So this means that I have not condensed E and E cube, but I can still have non-topological local operators transforming in charges E and E cube. So let me call them as deconfined charges that remain in the system. So if these are my set of condensed charges, then I have some deconfined charges over here, E and E cube. And the ones that are not mutually local with the condensed ones, those ones I will call as confined. So I'm trying to borrow terminology from Meissner effect in superconductivity, which may also be familiar from monopole condensation in Seiberg-Witten theory. So if you have something that condenses and you have some charge which is non-local to it that gets confined, while the charges which are not non-local, which are local to it, they remain deconfined. So in this case, there will be some confined charges like M and M cube, but M squared will be part of deconfined list. So one can imagine you have a phase of this kind. There's some deconfined charges which were generated by non-topological operators. So this would be some sort of a gapless system again. So this will be gapless. But with the key property that you still have something which is condensed. And that's going to, you can measure this operator. So this gapless phase is going to split into 2 universes, depending on what the value of E squared is. So this is a gapless theory with 2 universes. So like if I denote the universes by 2 crosses, the Z4 symmetry is going to act like this. The generator of Z4, P, is going to exchange these two, while P squared keeps you within each universe. And this P squared could be, so in each universe, there is some conformal field theory, and this P squared could be a Z2 symmetry of this conformal theory. So you can imagine that you have 2 E-sync CFTs sitting over here, and that would describe such a gapless phase for Z4 symmetry. So So notice that this is a very canonical generalization of what a gap phases are, where these crosses are just trivial TQFTs, 2D TQFTs, which are also called as vacua. But now instead of having trivial 2D TQFTs, we have some conformal blocks. And then there is some spontaneous breaking that can move you between these conformal universes. Are there any questions at this moment? Okay, so let me continue with this line of thought over here. One can ask, what are all the possible phases in this fashion? So we can condense all of these. We can condense 1 and e squared. One could have also condensed 1 and m squared. And this will again be gapless because there will be some deconfined stuff around. For example, e squared will be deconfined. But there will be no extra universes. All it's telling us is that p squared is trivial inside this. So we have a conformal field theory in which Z4 acts by a homomorphism. So we have a homomorphism from Z4 to Z2. And this Z2 is acting on a conformal theory. So that's how the Z4 symmetry is realized with a single universe. And then there is a very interesting phase. One can also take just this piece inside of it. So one can condense a combination of e squared and m squared. So what this now means is that we have p squared can be made trivial by a local operator in the infrared, which is topological. But this local operator carries a charge too. So in this case, again, there is some sort of a homomorphism from Z4 to Z2 that's acting on the infrared CFT. But because of this property, this Z2 is actually anomalous. Yeah, so this Z2 has a 't Hooft anomaly. And there are in 1 + 1 dimensions, there are precisely 2 't Hooft anomalies. One is the trivial one is the non-trivial one. So this is the non-trivial one, which is being realized on a CFT. Okay. Yeah. So one can also ask now, what about, so we have now started to understand if I have a Z4, if I have a system with Z4 symmetry, what are the possible phases that can arise, whether they are gapped or gapless in the phase diagram. But can we say something about moving in the phase diagram? Can we say something about possible phase transitions that can exist? Or what are the possible deformations? So this is quite easy to understand. So let's say you are in 1 comma e squared. You have already condensed e squared. You are in this gapless phase, and you want to move on to some other phase. You certainly cannot condense m because that no longer exists, is confined. You don't have it available anymore, but you can condense something in your deconfined list. So you can either condense m squared and go to the Z2 SSB phase, or you can condense E, in which case you cannot condense m squared simultaneously, but you go to Z4 SSB phase. So this gapless phase can admit, so if you have a theory in this gapless phase, it can admit deformations to Z4 SSB or Z2 SSB. Now, this is not to say that dynamical, there will definitely exist such deformations, but these are all just the possible choices. So all these possible choices can be organized in terms of a Hasse diagram. So let me draw the diagram. So on the top, you just have nothing condensed. So you're imagining that you have a phase in which all the possible charges are carried by non-topological operators. Then you can condense something. So you can have e squared being condensed. You can have m squared being condensed and e squared m squared being condensed. These are 3 gapless phases that we just discussed. And you have 3 gapped phases at the bottom. So you can have this one, the three gapped phases. And then the deformations are, the possible deformations can be described by arrows between them. So you have a picture like this. So if I just write down how many vacua we have, so here we have one vacuum. Here we have two vacua. We have four vacua here. Then the number of universes over here are 1, 1, and 2. So I just want to focus on this particular phase, which we encountered over there. Note that this is quite an interesting one because there is only one deformation which is possible for this. You have a single universe, and then the only gap deformation increases the number of universes. You end up having two vacua. It's not possible to go to a phase with a single vacuum. And this type of thing is very interesting from the point of view of condensed matter physics, because because this gives you a way to construct symmetry protected criticality. So you have some criticality which cannot be, you cannot lose that criticality unless you either explicitly or spontaneously break the symmetry. So without breaking the symmetry in some fashion in the infrared, you preserve the criticality. And these kind of phases are very popular. They go under the name of intrinsically gapless SPT phases, which I believe people in the audience have also worked on. In particular, Yunchin has worked on this. So I just wanted to mention this. Okay, are there any questions? Okay. So now I want to extend all of this to categorical symmetries. So I should say that these categorical symmetries became very popular after a paper of Kaidi, Omori, and Zheng, and other papers by Shu Hang and Sahand, etc. Very recently, where they started to understand non-invertible symmetries in high-dimensional quantum field theories. Before that, a lot of work had been done by myself and many other people, including Zohar, in trying to understand how symmetries can be used to constrain the dynamics of 1+1 dimensional quantum field theories. I mean, like non-invertible symmetries. And there has been a lot of work done before for invertible symmetries. Yeah. So yeah, now for the moment, I want to remain in 1+1 dimensions and generalize to fusion categorical symmetries. So let me give you a brief overview of how these symmetries look like. So we have a fusion category. And the essential data inside of it are some what are known as simple objects. So we have some simple objects, let's call them A. The symmetry category is S. And these describe various simple symmetries that you can act on the system. So in the case of Z2, this was 1 and P. For Z4, this was 1, P, P squared, and PQ were the simple objects. But you can have more general simple objects. Then there is a composition of the symmetries, which is described by fusion rules in this category, which is described by some sort of tensor product. So for group-like symmetries, the tensor product always takes this kind of a form, where you only have one simple object on the right-hand side. But for non-invertible symmetries, this can be generalized. So you can have instead a sum of symmetry elements on the right-hand side. And that's what makes it non-invertible, because now it has to be written as a non-trivial ring and cannot be reduced to a group ring. So there are some simple examples. So as we already discussed, any group gives a fusion category. These categories are known as G-graded vector spaces and denoted by vec G. There's another type of symmetries which are obtained by gauging this G symmetry, which are known where you, after gauging, you obtain Wilson lines. And since these are discrete groups, the Wilson lines are topological. So they generate a fusion category known as rep G. And the simple objects here are irreducible representations of the group G. And then the fusion rules are simply the tensor product decomposition of these representations. And as you will know that if we pick G to be non-abelian, there can be irreducible representations of dimension bigger than 1. There have to be, in fact. And these representations cannot be invertible simply because the dimension will increase. So the simplest example of such a group, the simplest non-abelian group is of order 6, which is the permutation group of 3 objects. And it has its irreducible representations are as follows. So first of all, there is the 1, which is the trivial representation where every element acts trivially on a one-dimensional vector space. There is the sign representation, which I will denote by P, in which any transposition acts non-trivially, but a cyclic permutation of 3 objects acts trivially. So transposition acts non-trivially, and the cyclic permutation acts trivially. And then there is a 2-dimensional representation E, which allows for cyclic permutation to act non-trivially. So you have 2 vectors V1 and V2, which are linearly independent. The cyclic permutation acts by omega, a third root of unity rotation on one of the vectors, and by the other third root of unity on the other vector. And then a transposition exchanges these 2 vectors. So this is a 2-dimensional representation. And then the fusion rules of these are given as follows. So first of all, P squared is 1. So there is a Z2 subsymmetry inside of it, inside rep S3. Then we have E times P is E. And E squared gives us a sum of this type. So this is one of the simplest examples of non-invertible symmetries. There are other examples which are studied in the context of duality defects, known as, for example, it's known as E-sync fusion category or Tambara-Yamagami fusion category based on Z2 with a trivial choice of the Frobenius-Schur indicator. So this one has some objects, 1, P and S. P generates a Z2 subsymmetry. Again, PS as P is S, and S squared is 1 plus P. So there is some difference in the fusion rules over here. Okay. So now we want to understand what are the possible phases for any such fusion category symmetry. So what do we want to actually understand? We want to, first of all, have a list of what are the possible charges that local operators can carry under such a symmetry. Then we want to understand which of these charges can be condensed. So condensable charges. So these must be mutually local with themselves. And then we want to understand possible subsets of mutually local. So subsets of, this is the full set of condensable charges. And then subsets which are mutually condensable. And we can then easily figure out which of these subsets are themselves subsets of each other, which will tell us what are the possible deformations. So let's start with point 1. How can I figure out how non-invertible symmetries act on local operators in a 1 plus 1 dimensional theory? Yeah. So here it's you don't have to do it, but it becomes easier to understand, to phrase all of the analysis that we have discussed so far in terms of what are known as symmetry TFT. So what is a symmetry TFT? The conjecture is as follows, that if I'm given any d-dimensional quantum field theory on which there is some symmetry S, which could be some fusion higher category that acts on it, such a system can always be recovered as an interval compactification of a one higher dimensional theory. The bulk of this theory is a d plus one dimensional topological quantum field theory, which only depends on the symmetry S. So let me call it, it's a function only of the symmetry S. One of the boundary conditions, which I will choose to be on the left, is a topological boundary condition, which also only depends on the symmetry S. And so it's known as the symmetry boundary condition. And it has the property that topological defects that generate the symmetry S all live on the left boundary. So all the topological defects which are generating the symmetry S just simply arise as images of topological defects living over here. And all the topological defects living on this boundary are given by S. So note that the QFT might have more topological defects than just S. But the boundary is fixed by the property that it has exactly S number of topological defects. And then on the right, we can have another boundary condition. If the theory is non-topological, this boundary is non-topological, and it captures the dynamics and the physical properties of the theory, which are not captured by symmetries. So this is known as a physical boundary condition. So given this conjecture, we can see how the Z2 and the Z4 phases arise from this. So note that if you want to classify just gap phases, it's quite easy. You can replace, you want topological theories over here. So the only non-topological element is on the right boundary. You can choose this to be topological boundary, and you can just classify topological boundaries of this TQFT. Yeah.
Sorry. I think you said the existence of symmetry TFT is a conjecture. Okay. How strong is the evidence for this conjecture in general?
Yeah, so we can recover all of these phases. So for example, I will describe how to recover gap phases using it, and also the gapless phases that we discussed.
Yeah, so for given symmetries, you can do that, but I think you are making a very strong statement, right? So for all possible QFTs, there is symmetry TFT. So you expect this to really hold to everything?
So this relies on this conjecture, yes. But yeah, you can also not rely on symmetry TFT and phrase everything algebraically. So if you want to discover the charges, you can just begin with the tube algebra, for example, as Andrea discussed, and you can try to classify what are the representations of tube algebra, and one will find that they're precisely how symmetry TFT captures these charges. So there is a lot of evidence about it, but it's still a conjecture, yes. But I would say it's quite strong.
Okay.
Yeah. Yeah, so let me illustrate how this works for the Z2 case. So when our symmetry was just Z2 symmetry, the symmetry TFT is what is known as the toric code, or the Z2 digraviton theory in 2 plus 1 dimensions. So it's the Z2 digraviton in 2 plus 1. And it can be described in terms of its anyons. So it has anyons which can be labeled as follows. where these two are bosons and this one is a fermion. And then one wants to understand what are the possible topological boundary conditions that such a theory can have. So these are described by what line operators, which anyons or these topological line operators of the 3D theory can end on the boundary. And there are two choices. So either they can be E-type boundary or they can be M-type boundary, because only a boson can end on a topological boundary. So you get the same kind of things as for the Landau paradigm over there. So you want only those anyons can end which are mutually local with each other. And in fact, this is not a coincidence. We will see that this is there is precisely a one-to-one correspondence. Right. So in one case, when you put BE over here, the symmetry boundary can be fixed to be one of them. We can fix it to be BE. In this case, one obtains a topological local operator by just spanning the E anion between the two boundaries because it ends on both of them. And one recovers the Z2 broken phase. There is a non-trivial topological local operator. And in the other one, M ends. So one has a system configuration like this, where now M cannot end on BE, but becomes the Z2 symmetry generator P. So one finds that there is a topological local operator living at the end of P, and this is precisely the trivial phase. So the symmetry TFT is able to recover all the phases that we discussed. But our task is to understand how the charges are encoded. So for that, let's return to the abstract discussion over here. Right. So there, let me redraw that one. So we want to construct some defects which can be charged under the symmetry. And the symmetry is completely localized over here. So there are two possible ways to construct these defects. Either these defects are living somewhere over here or somewhere over here. If they're non-topological, they must live over here. So let's restrict to this case. But in that case, the symmetry, they completely don't talk to the symmetry. So they're not the ones which are charged. So we don't need to worry about them. How can we make the defects living on the left boundary talk to defects living on the right boundary? Is by constructing it as kind of a compactification. So if I take a topological defect in the symmetry TFT, end it on the right and end it on the left, then I get, so if this is Q plus one dimensional, then I get a Q dimensional defect. But now it talks to the symmetry topological defects. So again, there is some topological end over here. This is topological, and this may be non-topological. And this one will be in general non-topological. So if I know my TQFT properly, I know its boundary conditions. I know the topological defects inside the TFT, and I know the topological ends on this topological boundary condition. All of this is a mathematical problem in category theory that can be worked out. So essentially, so now we have constructed a non-topological operator, and its transformation under the symmetry is completely known because we know how the defects living on this boundary, left boundary, interact with this topological end. So this gives us a way, and note that any non-topological defect constructed in this way will have the same transformation properties, or it will have the same charge. So the only information that went into it is just this Q plus one dimensional topological operator. So from this abstract argument, we can argue that Q dimensional charges or charges of Q dimensional operators are the same as Q plus one dimensional topological operators of the symmetry TFT. In 1 plus 1 dimensional case at hand, Q is 0 because we're looking at charges of 0-dimensional operators. So we are looking by this correspondence, we want to look at 1-dimensional topological operators of the symmetry TFT. And this is precisely what happened over here. So the anyons were E and M that could be condensed. And these correspond precisely to the sigma operator and the mu operator, or a charged operator and a twisted sector operator. And this can be generalized to groups and other fusion categories. Now, so we can generalize this now to any fusion category. If S is a fusion category, Z of S is the Turai-Viro QFT built on S. Its anyons are what are known as, or the topological line defects inside of it are given by the Drinfeld center of S. And then this Drinfeld center description tells us how precisely the symmetry S acts on these operators. So let me give you an example that because this can be quite interesting. In the group case, we saw that either we can have charged operators or we can have twisted uncharged. And they do not mix with each other. But as soon as we have non-invertible symmetries, these mixings can happen. So one can have charges where you have charged operators mixing with twisted uncharged operators. So untwisted and twisted sector operators come together in a single multiplet. And an example is given by one of the multiplets. So it's, for the lack of a better word, it's called the A multiplet, because it comes from an anion which is described by, so it comes from an anion which is described by a conjugacy class inside S3. And the A stands for the cyclic permutation over here. So it's conjugacy class of cyclic permutations. So this one has two operators. There is a untwisted one, and there is one which is twisted, which lives at the end of the Z2 symmetry generator. And then these two are exchanged. So if you take the line E and move it across the untwisted one, you obtain an interesting relation of this form. So you get -½ times the untwisted operator, but plus omega plus half times the twisted operator. And no, it's these two form a representation of rep S3. It's just untwisted operator. In rep S3. So my symmetry is rep S3. So I should say, have said S is rep S3. So I want to describe what happens in this non-invertible case. So there is this interesting action of the symmetry of this form. Okay, so using this and using just category theory, understanding the Turai-Viro theory, one can completely understand what are the condensable anions. One can carry out this whole list. The point 1, 2, and 3. So for the point 2, so in our case, we understood that the list of charges is just the Drinfeld center. For point 2, these are all the possible condensable charges would be some what are known as condensable algebras within. Okay, so let me just describe what are the subsets of mutually condensable charges. These are condensable algebras in this Dirichlet center. So if I call this Dirichlet center Z of S, so for example, we had for the Z2 case, we had an algebra of the form 1 plus E, 1 plus M. For the Z4 case, we had 1 plus E squared, 1 plus E squared. So these are some examples of condensable algebras. And essentially how you find them is by looking at what are my simple anyons, what are their spins, and their braiding properties. So you want their spins to be trivial, you want all of them bosons, and you want them to not mutually braid trivially with each other. Yeah.
From at the end, well, down finding which are gaugeable algebra.
Probably, yeah. Yeah, I think so, yeah. Yeah, and then, yeah, I think that's precisely what's going on. So if you gauge this thing, then you get, so in general, a condensable algebra describes a topological interface from my symmetry TFT to some other topological QFT. And then these anyons in the condensable algebra can end over here. So I think these are precisely the ones which are getting gauged, and you get Z prime as the gauge theory of gauging this. Yeah, I think you're right. Okay, right. So one can figure all of this out. So let me present to you the results for rep S3 symmetry. So one can draw a diagram similar to that for rep S3. Yeah, so first of all, we have our one, which contains all kinds of charges, which is a gapless theory containing all kinds of charges. Then we can have something like this, where we have two universes which are exchanged by the non-trivial symmetry E, the non-invertible symmetry E. E has some sort of some complicated action, so it can also take this universe within itself. And then we have the Z2 symmetries, which are acting within these universes. Then we have another gapless phase where the whole of rep S3 acts within it, but it's somehow realized by a homomorphism to a smaller symmetry. And then we have another one of this type. We choose different homomorphisms of rep S3 down to Z2 or rep S3 down to Z3 in these two cases. And then we have gapped phases. So these are gapless. Then we have some gapped phases, which have some interesting properties, which have so there is one gapped phase of this type. Then there are so we can have three vacua in which if you just focus on the Z2 subsymmetry, then it looks like you have a ferromagnet plus a paramagnet. So note that if you did not know about the non-invertible symmetry, you would be perplexed why you have, if you had a model which was realizing it, you would be perplexed why you had a ferromagnet and a paramagnet sitting together, because you just have a Z2 symmetry. And in fact, this is a phase diagram. This is a whole phase that can arise in a lattice model, which can be realized. And you will see that even if you deform your parameters, you cannot get rid of this degeneracy. So this degeneracy can only be explained if you know about the full rep S3 symmetry of that lattice model. Similarly, over here, you have three paramagnets sitting together. which you cannot explain. The degeneracy cannot be explained unless you invoke the Rapace-3 symmetry. So there are two more phases which are just ferromagnetic, just two and one paramagnetic one, which can be explained just by Z2 symmetry. But there are two new phases that you acquire that arise from the existence of this non-invertible symmetry. Similarly for gapless phase over here. So here you could have seen an E-sync CFT because you need a Z2 symmetric CFT, but you would see two E-sync symmetries, two E-sync CFTs sitting together, degenerate with each other. And if you just know about the Z2 symmetry, you won't be able to explain why they are degenerate. And along some higher codimensional submanifold in your parameter space, this phase will, gapless phase will exist. And here this can be just described by three-state pots and E-sync CFT. So there is, using traditional Landau, you won't have a problem describing them. So these are the three interesting things one finds, which can only be explained using non-invertible symmetries. So note here the deformations again. So there is something interesting going on. This one has only these two deformations. And you can note that this has two universes, but the number of universes increase after deformation. So this is an extension of what are known as intrinsically gapless SPTs that I mentioned over there. And they can be called, so we dub them as an intrinsically gapless SSBs. Okay, so I think I have mentioned.
I have just a really basic question. So is the notation here, so the two dots are two separate vacua, and then they're supposed to be, for example, mapped to themselves with P and mapped to one another with E? Is that, but then so for the right one, if I act with E, what happens? It seems there are two arrows.
Yeah, so it goes into this one plus also into this one. So it goes into the sum of the two universes.
Oh, I see. Okay.
Yeah. Okay. Yeah.
This diagram is particular for the 1+1 dimension.
Yes,
One dimension. But at which step you used that fact? I'm
yeah, because I
Yes.
was working with fusion 1 categories.
Yeah.
So the one in that indicates that you are in 2 dimensions. And also my symmetry TFT was 3-dimensional. It was described by ions. Yeah. So that also means that I was in 1+1 dimension.
You used those information.
Yes.
Thank you very much.
Yeah. So let me quickly describe extension of this to higher dimension. It becomes much more interesting in 1 higher dimensions. So let's take the simplest example of just a Z2 symmetry. If I have G is Z2, the symmetry TFT is now 4D or 3+1 dimensional Z2 digraviton theory. And it has some surfaces and lines now instead of having 2 lines. So the E is a line, E operator is now a line, and the M operator is a surface. You also have condensation defects for this line, but they don't play an important role in what I'm going to talk about. And now you can ask, let's just classify gapped phases. So we want to just classify gapped phases. So note that in 1+1 dimension, we obtained a finite set of gapped phases. We classified topological boundary conditions of the 3D TFT. There were a finite number of them. But now in 4D, when you go to 4D TFTs, the number of topological boundary conditions become infinite. So there is one rather naive infinity, which just comes from, so if I have some boundary condition of this 4D theory, I can always stack a 3D TFT. This is a very naive one, but even if we mod out this one, there is still an infinite number of them, which cannot be separated out into a boundary condition times a 3D TFT. So let me describe the structure of them. So this was discussed in our recent paper, in a recent paper of ours. But yeah, what is the general structure? So the general structure is to begin with the Dirichlet boundary condition. on which the line E can end, but M cannot end. So it generates a Z2 symmetry in 3D. The M surface operator becomes the generator. And then we tensor it with a 3D TFT, but now it's a Z2 symmetric 3D TFT. And we mod out, this has a Z2 symmetry, this has a Z2 symmetry, we mod out a diagonal Z2, which couples them together. And there are an infinite number of Z2 symmetric 3D TFTs. As you may know, like because there are infinite number of 3D TFTs given by topological orders, you can have various MTCs. So there are, and then you can extend them. If you want a Z2 symmetry on an MTC, there is a notion of what is known as a Z2 crossed braided extension of the MTC. And these are also infinite in number. So you can input any of these things over here and carry out this construction. You obtain an infinite number of topological boundary conditions. You may ask, what are the symmetries these correspond to? This is quite interesting. So yeah. So here, the symmetries of the following form. You have a Z2 one form symmetry because you gauged a Z2 zero form. But this Z2 one form sits non-trivially, it's extended actually. So it sits non-trivially inside an MTC. Such that if you look at what are the, not MTC, sorry, a braided fusion category, which is not modular. So a braided fusion category, such that if you ask what are the completely invisible lines inside of this braided fusion category, or what's the non-anomalous part of it, which is known as the Muger center and denoted by Z2 of this braided fusion category, this is precisely the Z2 one form symmetry. So it's there are infinite number of anomalous extensions of non-anomalous Z2 one form symmetry, whose symmetry TFT is the same as for the Z2. And one can then now pair these two boundary conditions on the left and right and get infinite number of gap phases for each of these types of symmetries. So the structure can be found in our paper. I won't go into the detail. I just wanted to mention it. And then this can be extended to other groups. But one interesting point is that you're almost done. If you just work with symmetry TFTs, which are Digrave-Witten theories for group G, possibly with a twist, a Digrave-Witten twist, that's half of the story in 3 dimensions, because there are mathematical results that tell you that every fusion 2 category can be gauged into this form, up to some fermionic thing. So I say half because there's some fermionic stuff to account for that as well. Okay, so right, I have only 1 minute left, so let me conclude. So we saw that there is a categorical Landau paradigm that one can describe. It generalizes the usual Landau paradigm in various directions. So it includes automatically the SPT phases. It includes topologically ordered phases in higher dimension. And it includes within it the description of order parameters for these phases. So what are the things that will condense? What are the charges that will condense? And also one can talk about phase transitions. So if one is looking for phase transitions between them, one will talk about, one can look at this order parameter and see which order parameter one needs to tune to go through the phase transition. There is something missing in our description, which is a Landau-Ginzburg type of description, which is still lacking, and we are working on it. So this, I described this mainly in 1 + 1 dimension, but it can be generalized to higher dimension where it becomes much more technical, but it can be done. It can be generalized within 1 + 1 dimension to different kinds of symmetries. So I assumed that I had finite symmetries, which are bosonic and internal. One can generalize them to fermionic finite symmetries, which are internal. This is a work we did with Kanse, Namura, and Apur Tiwari. Where one just looks at, so the symmetry boundary is obtained by condensing fermions rather than bosons in the symmetry TFT. One can generalize it to other kinds of symmetries like time reversal symmetry, which is work in progress. And including it with fermions, one can obtain pin plus, pin minus kinds of systems. Okay, so thank you very much for your attention. Yeah.
So in the 1+1D case, I just wanted to understand what can we learn about 2D CFTs from this way of thinking? I mean, isn't it sort of the original the original result of Witten that Chern-Simons theories have a 2D CFT on the boundary? Is that like a special case of these diagrams that you have been drawing with one topological and?
That's a slightly different setup. So in that case, the 3D TFT does not admit a topological boundary condition in general because it has a chiral central charge. This ones have chiral central charge 0, so they admit topological boundary conditions.
I see. But okay. But so you're saying if there is a chiral central charge, then there's no topological boundary condition.
Yeah.
But there's still there's some sort of construction, right, where people study sim TFTs with two boundaries that are dynamical and one topological boundary in the middle. Is that sort of?
Yeah, so yeah.
I was told that corresponds to combining left and right movers to make a modular invariant.
Yeah, so that's the standard Moore-Seiberg story.
Right.
This one is slightly different because it requires topological boundary conditions. It's quite similar, but it has different.
It seems like this is like half of that story in some way, right?
Yeah. Or one way is you can double it. So if you double such a thing,
Exactly.
the chiral center charge cancels.
Okay.
And you obtain a topological boundary condition where you fold.
Right. Okay. So in some sense, that version, the old Moore-Seiberg version, is a double of this kind
It's a square root of this one.
That's the square root of this, or this is the square root of that?
That's the square root of this. So if you double that one, then you can obtain topological boundary condition.
Okay. Thanks.
Any other questions?
So this richness of 2+1D system seems to come from that richness of 3D TKFT. And what about, for example, 3+1 dimension? Does it become simpler?
Yeah. So I don't know the classification of 4D TFTs, but I expect that there's also again some topological order. So you can have lines and surfaces that can combine with each other, right? So
in the case of, for example, 3+1D TKFT with, for example, with one form symmetry are expected to be a kind of gauge theory, right? And so does this kind of information give a restriction for possible, for example, gap boundary?
Yeah, they should, but we haven't explored it. So I actually use this restriction over here when I said that this is half the story. The 4D theory is always expected to be a gauge theory up to some fermionic ingredient as well. Yeah, so we used it as a symmetry TFT, that if you just use these gauge theories in 4D as symmetry TFTs, then you can understand all possible symmetries in 3D. But you're suggesting we can also understand gapped phases in 4D using this easily. Yeah, so I think that's will be nice to explore. Yeah. No, this was for finite symmetries. Yeah. Yeah. It is technical for this work because we want to say if you have a finite group symmetry, the symmetry TFT is a topological theory, right? You have a gauge theory based on finite gauge group. For continuous ones, I would expect their gauge theory is based on continuous gauge group, so they would be non-topological. So yeah, they will be more harder to understand. But I think there has been a lot of work done in the literature recently. In the last few months, there were many papers trying to describe symmetry TFTs for continuous symmetries. But I'm not an expert on that. Yeah.
Any other questions? Okay, if not, let's thank Laksha again.
Thank you very much.